Okay, let's get started. My name is Sydney Hunter, and I'm a marketing specialist here at Usalco, and I'm excited to introduce the webinar today. Usalco is the premier manufacturer of various aluminum and iron-based chemicals. Usalco's polyaluminum chloride products, which are DelPAC and UltraPAC, have become the coagulants of choice in well over 1,000 water treatment applications throughout the United States. Usalco is headquartered in Baltimore, Maryland, which is also the site of the largest aluminum coagulant manufacturing plant in North America. Usalco operates 26 manufacturing facilities throughout the United States. Today, we will be presenting on the topic of using the total treatment cost method to compare coagulant programs. This topic will focus on the idea that cost per unit of treatment additives is part of the value equation, but the total cost considers multiple factors and gives a more complete and useful picture. This webinar is part of an ongoing series of presentations meant to bring valuable knowledge to the marketplace. Today, I am pleased to introduce our presenter, Chris Lacey. Chris has been in the water treatment industry for 12 years, and he focuses on technical sales and marketing. At the end of this presentation today, we will have time for questions, and if we don't get to your question in this time, we will provide contact information to start the conversation offline. So at this time, I'm going to go ahead and turn it over to Chris Lacey, our presenter.
All right, thank you, Sydney. Appreciate everyone joining. Welcome to our webinar on how to use the total cost method to compare coagulants. We appreciate you taking the time out of your day to tune in with us. We hope you find this time helpful. We're recording this event for distribution on LinkedIn and YouTube and prevalent podcasting platforms, and we'll post this in coming days on those. Let's go ahead and talk about the objective of this webinar. The goal is to inform participants on how to evaluate the overall cost of treatment methods when comparing different chemical products. This approach provides a more comprehensive understanding of the value each product or treatment program offers. In the field of water treatment, specifically regarding coagulants, many stakeholders may not be familiar with the method for effectively comparing conventional coagulants to specialties. This concept can be complex, especially for those new to contrasting chemical programs, which is why we put this together. As for the agenda today, we're going to introduce Usalco. We're going to cover a familiar total cost example that everyone who's purchased an automobile has at least considered, and then we're going to dive into coagulants. So let's go ahead and start off with our automotive example. Actually, let's go ahead and talk about Usalco and some quick notes. So Usalco operates 26 manufacturing plants between California and Maryland, down to Puerto Rico and back over to Texas. We supply the coagulants for over 1/3 of Americans and ship over 40,000 orders annually. So let's go ahead and dive into that automotive example now. So let's discuss a common scenario, particularly one that car buyers consider. And let's set it up. The buyer is looking for a new vehicle and they commute approximately 400 total miles weekly. They will use the vehicle for other common travel uses outside of commuting, and the buyer has a spouse with children, and the current gas price is $3 a gallon. Now let's consider a Toyota Yaris and a Range Rover as the two possibilities and two very different vehicles, especially for commuting. The Toyota Yaris travels 37 miles to the gallon, whereas the Range Rover covers 21 miles per gallon. So the Range Rover needs around 19 gallons of gas to travel 400 miles, which amounts to $57 per week for the Range Rover, while the Yaris requires about 10.8 gallons to travel 400 miles, which amounts to about $32 a week for the Yaris. And this translates into a savings of approximately $639 when commuting with the Yaris annually, which is a 43% fuel cost reduction compared to the Range Rover, or 3 cents a mile. However, this decision-making for the buyer extends beyond fuel efficiency, right? There are other costs to consider as well, and they should also be considered to generate a total use cost for each vehicle. Cost factors such as the purchase price, maintenance costs, insurance costs, safety ratings, and extended warranty can be crucial. And then every buyer will also consider less tangible factors like the cargo space, the driving experience and appearance. And these factors can be even more important when costs are not the primary purchase factor. And vehicle buyers will prioritize these factors differently, leading to the varied preferences we see on the roads today. So how do we apply the same economic concept to coagulant chemistry? This logic is applicable to the field of water treatment as well, with some unique considerations because we're going to be contrasting coagulants. So first, we need to generate metrics to contrast. And the first way to do that is to begin by bench testing. It is necessary to conduct thorough testing of coagulants in a controlled environment that mimics the actual water treatment plant's conditions. This step is essential to identifying the most effective product. Replicating the mix energies and mix times are crucial to ensure the data is representative. The second is representative trials. Implement a trial phase with the selected product in the actual plant for a duration of at least 1 to 4 weeks. This goal of the trial is to generate real-world performance data and understand what the impact on the process will be. Variables such as DOC removal performance, filter run times, and pH chemistry demand are oftentimes the most crucial metrics to track before and throughout a trial. And then 3, run a total cost analysis post-trial. Analyze the data to calculate the total cost of treating 1 million gallons of water with both the incumbent and proposed coagulant. So let's introduce this concept of specialty coagulants to ensure everyone understands how and why optimizing a program may be necessary. There are 3 key components to consider when selecting a coagulant for any application, and all 3 correlate with overall efficiency. So first, the type of metal salt, specifically whether it is aluminum or iron. That question may be answered by considering the hardness of the water source or the proximity of the manufacturer to the site. A lot of times, users will use a particular product because the manufacturer is very close to the application point, and that's the only coagulant that they've ever used at that facility because of that. Second is metal content. Maximizing the metal content will bring down the dose fed or the total amount of coagulant required to meet the treatment goals. And then third would be the basicity of the product. What is the optimal basicity for the product, which requires the lowest dose and yields the most efficient performance? This concept applies to drinking water and most wastewater applications that require coagulants. So as an example, you can see here aluminum sulfate, which is one of the most prevalent coagulants on the market. Alum has a low metal content for a coagulant with no basicity. While this product performs in a wide range of applications, it is rarely the most efficient available option. DelPAC 3030 is a Usalco specialty coagulant that works particularly well for drinking water treatment, and like alum, it also performs in a wide range of geographies. And where the basicity is optimal, it can outperform an alum program. As you can see, the metal for alum is at 8.2%, which is like the active ingredient that causes the reaction, while the DelPAC 3030 is at 14.4%. The metal concentration being used to generate the reaction is 75% stronger than the aluminum sulfate, which drives the overall efficiency of the coagulant. So let's move over to the coagulant comparison example now, and let's dig into that. Let's say that the plant's current program is aluminum sulfate, and they feed 60 parts as is liquid. They're considering a polyaluminum chloride, and during bench testing, they estimated 22 parts. And for the optimum dose, and then during the plant trial that ran for a month, they found that they met all their water quality goals at slightly lower at 20 parts. And they were feeding 13 parts of 50% caustic, also known as sodium hydroxide, when using aluminum sulfate. And they feed this for pH control. They also found they would require 7 parts of 50% sodium hydroxide while using polyaluminum chloride. The average plant production is 30 million gallons per day. And we have our example costs at 8 cents per liquid pound for alum, 25 cents per liquid pound for polyaluminum chloride, and 14 cents per pound for 50% sodium hydroxide. So how do we contrast the 2 products? We determine the cost of each coagulant per day and then divide by the water production for the day to generate a total cost per million gallons treated. For this example, we use a 30 MGD plant, 30 million gallon a day plant. And let's begin with the incumbent aluminum sulfate program. If they feed 60 parts at 8 cents a pound, we calculate the pounds per day required first. We take the 60 parts multiplied by 30 million gallons a day times 8.34, which is the weight of a gallon of water, and that would equal 15,012 pounds per day. We then multiply the pounds per day by 8 cents a pound, which is the cost of alum, would equal $1,200.96 per day. We then take the $1,200 and divide it by 30 million gallons, the plant production of 30 million gallons a day, and that would equal $40.03 per million gallons. For the polyaluminum chloride program per day, they feed 20 parts at 25 cents a pound. We then calculate pounds per day by multiplying that 20-part dose by 30 mgd by 8.34, would generate 5,004 pounds per day for the pack. We then take the 5,000 pounds, multiply it by 25 cents a pound to generate our cost per day of $1,251. And then we then divide that by 30, which would then equal $41.70 per million gallons treated. We now have our two coagulant costs. For this scenario, we also calculate the sodium hydroxide demand difference between the two programs because that can be substantial. When feeding alum, the plant feeds 13 parts at 14 cents per pound. We calculate the pounds per day by multiplying 13 parts by 30 mgd by 8.34 would equal 3,252 pounds per day. We then take the pounds per day, multiply it by the cost of the caustic at 14 cents per pound, would equal $455.28 per day. And then we then take that and divide it by 30 mgd, which would equal $15.18 per million gallons for the caustic soda. When feeding polyaluminum chloride, the plant requires 7 parts, so a lower dose, at 14 cents per pound. We calculate the pounds per day by factoring 7 parts by 30 mgd by 8.34 will be 1,751 pounds per day. We then multiply the 1,751 by 14 cents per pound to equal $245.14 a day, divided by 30 mgd, which would equal $8.17 per million gallons treated for the sodium hydroxide. Finally, we carry over our numbers from each coagulant and the caustic cost calculation to generate a total treatment cost. Our alum program cost example of $40.03 added to the $15.18 for the caustic would equal $55.21 per million gallons. And for the polyaluminum chloride program cost, our example of our scenario is $41.70 for the PAC program plus $8.17 for the caustic soda portion would equal $49.87 per million gallons. The difference is easy to generate. We just subtract the total alum cost by the we subtract the PAC cost from the alum cost to generate $5.34 per million gallons treated. We then take 30 mgd, we multiply it by 365 days in the year to generate the total plant production for the year of 10,950 million gallons, which is about 11 billion gallons of water per year. For this scenario, the treatment plant would save approximately $58,473. Now, as we discussed, using the total treatment cost is an effective way of comparing the economic variables while ensuring they are on a level playing field. This helps make it possible to compare apples to oranges. So in summary, when comparing coagulants, it's not only the economic variables that should be considered, customer service, reliability of supply, sludge handling characteristics, which often help improve labor and chemical costs, labor savings due to less chemical deliveries and equipment maintenance, improved safety posture due to less deliveries and subsequently less handling and maintenance of chemical equipment, less wear and tear on the filter media and equipment, as well as water savings and overall electricity savings. Ultimately, the focus is on determining the best value for treatment by considering the total operational costs, not just the initial price of the chemical. This comprehensive evaluation helps in making informed decisions when updating a coagulant program. Thank you so much for joining us. If you would like a copy of this presentation, please follow the supplied link. To learn how Usalco's network of specialists can assist you, please reach out at the link attached. And let's open it up for questions now. Please email those to webinar@usalco.com. And also, if you'd like a copy of the deck today, please send that request also to webinar@usalco.com. And I'm going to flip it back over to Sydney now to handle the Q&A portion.
Okay, thank you, Chris. We have received a lot of great questions. I was able to consolidate the incoming questions so we can get the most useful questions answered for you all. We'll start with this one. How does the metal content of ferric sulfate impact the total cost calculation?
Okay, so Well, because it's iron, the optimal process pH will be higher than it is for alum or polyaluminum chloride. So it's going to be a higher pH required. So another factor that would likely be added to the total cost analysis would be lime. And the lime would be used to help boost that pH up front. So a lot of times, at least down in Texas in particular, you see lime a lot being used with ferric sulfate. So the analysis would be run with a coagulant, the lime, and caustic. A lot of times they're feeding both lime and caustic at these sites, and the caustic dose also is also always impacted if it's being used. So that would be an additional chemistry to be considered. Good question.
Okay, thank you. We'll move on to this next question that we have. Would ACH be more efficient than DelPAC 3030 because the metal content of ACH is 23%?
Well, sometimes. So that's a great question. And it's always going to depend on the process water and what coagulant basicity is optimal. So there's a wide range of basicities, and ACH is at that very top of the basicity range, right? So the basicity of ACH is 82.5, 83%. So ACH is similar to alum in that it will work for a lot of different applications. And also like alum, it's not usually the most efficient option available. So when the most optimal basicity is found, less metal would subsequently be required in that instance. So in that instance, DelPAC 3030 would be more efficient than ACH. And that's how you
Okay,
would get to that. Yeah.
thank you. We'll move on to the next question now. If we have a small 500,000 gallon a day water plant, will Usalco send someone to help us try a new coagulant?
Absolutely. This typically is handled based on geography and our, and schedules. So quite often we'll match our opportunities to local technical specialists, and most of our production actually is managed through distributors. And so we've partnered with technical distributors across the United States, and they specialize in coagulants and water and wastewater treatment. So oftentimes we'll match up opportunities with one of them, and then a Usalco employee will handle it themselves. So yeah, that's usually how that works.
Okay, sounds good. And next question, can changing coagulants impact PFAS removal?
So yeah, good one. So very top of mind for everyone right now, right? Coagulants have been shown to remove PFAS molecules at varying chain lengths. It appears that larger chains are easier to settle out than smaller chains. And while traditional coagulant tech isn't likely to be a standalone solution for removing PFAS, it will in all probability be part of a solution. So that includes, additional polishing technology in order to meet treatment goals. I know we've started here at Usalco a major R&D effort to determine the effects of various proprietary coagulants on PFAS, and we're going to host a webinar in the future to share, what we find out about that.
Okay, thank you for that answer. Next question, can you supply PAC into Orange County, California?
Oh, absolutely, yes, we can. We have a plant in Modesto, California, which is in the Central Valley of California, and there we manufacture a wide range of PACs, polyaluminum chloride products, as well as ACH. Yes, that's not a problem.
Sounds good. Next question, are storage and piping requirements the same for alum and PAC?
Fortunately, yes, they actually are. I would say a caveat is with pumps, you're always going to want to double check the kits used to ensure they're 100% compatible. So I know that depending on the manufacturer, sometimes that kit will vary from pump to pump. So you always want to double check that no matter what. I know ferric sulfate and PAC are different kits for pumps, for example. So those would need to be swapped for sure, for certain. PAC and ACH require the same types of tanks. So a poly or a fiberglass tank, along with the same piping materials. They're perfectly interchangeable. So yes, the requirements are the same for alum and PAC. Most important is washing out the tanks and lines before loading PAC into an alum tank. They can react with each other and cause solids that can plug lines and valves. So that's an important thing to do, is just flush out the tank, flush out the lines, flush anything that might touch the coagulant out, even the dead ends or anything else that exists. You want to make sure everything's flushed thoroughly before converting.
Okay, good answer. All right, last question that we have today is how long does take to find the best pack option?
Can you repeat that?
Yes. How long does bench testing usually take to find the best pack option?
Thank you, Sydney. Okay, so how long does bench testing take? So, okay, so this is going to vary based on the type of application and the treatment goals. The first part of bench testing is replicating the current program at the bench. So this way you've established a control to test against. And that can take a day or two to accomplish sometimes, depending on the complexity of the treatment process. Once that control procedure is found, then the testing of the base specialties begins. And this can take another day or so, usually. Um, Once that basicity is discovered, then we would then optimize the pack within that range. And this part can take a few more days, so 2 or 3 more days usually. And additionally, some sites are very seasonally challenged. So, for example, the water may be completely different from the winter to the summer months. And so that could then add a couple more days if you need to go back and reconfirm in a different season to make sure that that optimal program for the hot winter months is going to work well in the coldest months, in the winter. So that's pretty much. So you're looking at about right around a week worth of testing. So, 5 to 7 days usually of business days of being in the lab working on it minimum.
Okay. Thank you. That was a great answer. And that concludes our Q&A session. Thank you all so much for attending our webinar today. And please don't forget to tune in to our LinkedIn profile and our YouTube account, where there will be a recording of this webinar posted. If there are any questions you have on applications or treatments, please don't hesitate to reach out. We want to help. Thanks again and have a good rest of your day.
Thank you all. Thanks, Cindy.